Hello. So, I am Prajit Banerjee, and I am here to teach a very important and interesting problem. Uh, so, let me explain first what is the problem. So, we are given a tree once. So, we are given a tree, and the tree contains certain values, maybe numeric values 10, 2, 3, 4, 5, 6, 7. And we need to find for each node how many of its ancestors have a greater value. For example, if we are at this node, we have to tell that how many of its ancestor, like ancestor, I mean its parent, grandparent, and so on. So its ancestor is 3, 2, and 10. So for 4, answer will be only 10. Similarly, if we go to this node 6, the answer will be this is maybe if this is let's say 100. So for 6, it will be 10 and 100. So answer for it will be just 1. Basically, we have to create an array for each node, and we have to store the count of each element's ancestors who are greater than the value of the node. So this is a pretty interesting problem. We can solve it in multiple ways, but I will try the most standard one, which is the depth first search. I already assume that everybody knows what a depth first search is. So for a beginner, let me explain what is actually a depth first search in very short, because I assume that most of you already know. So if we are given a tree, there are multiple algorithms by which we can traverse the tree or a graph, maybe. But in depth first search, we just go directly to any adjacent node we encounter. For example, if we are at this node, we will just directly jump into this or maybe this node. It completely depends on the implementation. So one second, let me see if the recording is, yeah, it is being recorded. Yeah, it is being recorded. Okay, fine. So one second. Okay, so it will traverse the graph or a tree in a depth wise manner. Like it will first go to this, and it will go to this, it will go to this. After the path gets exhausted, it backtracks and it goes back to its parent, and again starts traversing its adjacent nodes. When the adjacent nodes completely gets exhausted, so it backtracks to its parent, and so on. So this is basically a depth first search. So I'm not going into very details. So it is practically the most common type of traversal algorithms which is being used to traverse graphs and trees. Okay, so our main problem. So let me write the question. Given a tree with with values, we have to tell for each node how many of its ancestors have greater value than it. Okay, so this is our question, and so the first question that comes up to our that comes up is, for example, we are at a particular node, and how we will determine who are the ancestor of this particular node. In this case, it is y and z. I am more generalizing it. It's y and x, but how we will know that it is y and z, because here can be multiple subtrees and all. So how we will eliminate this part, and we will consider only these two parts. So we have a very like trivial technique to solve this problem. So whenever we are entering a node, one second, whenever we are entering a node, we will store it in some data structure, maybe an array. Okay, so we will store it inside a data structure, and we will continue moving in a depth first manner. And whenever we reach y, we insert y. Whenever we reach x, we insert x. So so like this we will keep traversing. And at this point you will observe that we have the ancestors of x in our array. But let's continue this example further. Now we backtrack to y and we go to, let's say, k. Now what will happen, x will get popped. Means when we are exiting a node, means basically when we are completely traversing a subtree and we are going out of it, we will keep popping the element. Now we will pop x, so x will get popped, and y will not get popped because till now we have not gone out of the node y. So now we are at node k, so we will insert node k. Now we can clearly observe again we got the ancestors of k, which is y and z. So it is quite trivial to store all the ancestors. So basically it will take order of n extra space, because for a skewed tree, maybe like this, for a skewed tree, let's say like this, it may have n nodes. Okay, it may have n nodes, and we will store all of them like this. But when we are using DFS already, we are using extra order of space, so it doesn't matter anyway. Okay, so now we know how to store all the ancestors inside a data structure. Now the question is, for each of these nodes we need to find out how many of them are greater than this value. So the most simple solution that comes up to our mind is that we will just traverse the entire array, and we will find that how many values are actually greater than n. So if we consider that this tree contains order of n nodes, means n nodes, then for each node the worst case time complexity would be order of n. I have already discussed it. When it will be skewed, then we need to traverse it again and again and again and again, like this. So the equation would become like this, that for the leaf we need to search n minus 1 elements. For its parent we need to search n minus 2, like this, like this, like this. It will be 2 and 1, so it will be approximately n into n minus 1 by 2. So its worst complexity is order of n square. So this is not a good solution, I mean not a very efficient solution. So here we will use a very what can I say, very powerful data structure, which is known as the segment tree. So as segment tree is a pretty advanced data structure, I am assuming most of you do not know about it. So I am giving you a quick introduction, and I will make a separate video about what is a segment tree, how the operations are actually implemented in the same segment tree, like update, query, and build, all these functions, and what are lazy propagations. So I will just give you a small introduction about segment tree, and then I will tell you that how we can use segment tree to solve this problem. So segment tree is a range is a data structure which is basically used to solve range queries. So what do I mean by range queries? Let's say we have an array which is maybe 10 to 5, 6, whatever the values might be. So if we are asked to find about certain subarray sums, then and we are given some queries. For example, we are given q queries. So this is also an offline thing, because first we will be provided with an array, and we will ask that let's say we will be provided with two indices, so let me mark the indices. So we will be given two indices, and we have to tell that what is the summation value of that particular subarray. Let's say we are given 2 and 4, so we have to tell that we have to output the summation value, which is 5 plus 6 5 plus 6 plus 7, which is 18. So we have to do it in an efficient manner. So the most trivial solution that comes up to our mind is the prefix concept, because it is quite trivial. Like we will initially pre-compute the prefix from here to here. I think I will not explain. Okay, let me write the prefix. Prefix is basically pre-computation technique where we basically store sums from the 0th index to the last index basically. Yeah, this is the array, so I'm considering it to be array A. Okay, so like we will just compute the prefix, and we will just subtract it, and we will get the answer in order of one time. So it is a pretty great method, but the problem starts when we are updating the index. So now let us modify this problem, and let's say we have q queries only, but now we have two types of queries. First query says that you find the summation between L and R index. This is the first query. And the second query says that you go and update a specific index. Let's we are given an index number, and we have to update a value. Now the problem starts. Whenever we are updating the index, then we have to compute our prefix again, because whenever, let's say for this one, whenever we are updating it 7 and 10, whenever we are updating a particular index, then the prefix values here gets completely changed. So if we are updating a value maybe at the middle or maybe at the beginning, then approximately it will take order of n time to compute the prefix again. So again we will need another efficient method to find these two queries. So now we use segment array. So I explained you what is the need of segment array, because many people think that we can solve all kinds of problems using prefix, but it is not. That's why segment tree has been introduced to us. Let's say so 10 to 5 6 7 10 11. So what we do here, when we are given the array, we build a tree with where each node, let me first draw. So each node contains a certain range sums. For let's say for this node contains summation from 0 to 0. This node contains summation from 1 to 1, from 2 to 2, like this. Now after creating all these nodes, we just combine them. So into 0 to 1. Now you have to understand that its value will be 10 and 2. See, the leaf nodes has a trivial value, which is 5 6 7 11, like this. But when we are combining, we are just doing the summation of the left and right values. So it will be 12, 5 and 6. It has become a little bit messy, so please don't mind. Yeah, it will be 11 and it will be 17, like this. We can combine this one and this one, 28. We can combine this, and ultimately we will combine this. So this is the tree which we can make by pre-computation, and as you can see, by mathematics we can prove that this total number of nodes might be approximately 4. Might be, one second, what is this? One second. Oh, yeah. So the what was this? Yeah. So the total number of nodes in this segment tree will be approximately 4n, where n is the size of our array. Okay, so there are pretty complex mathematical calculations by which we can show that maximum number of nodes might be 4n. So the build operation is order of n. So what do I mean by build operation? By build operation, we can create the segment tree. So the question is how we will store this tree. So we can store it in multiple ways. Maybe we can create a specific node, like when we solve binary tree problems, we just take left and right pointers like this we can do. But the most common implementation is we will just take an array. Yeah, we will take an array vector in an array, and we will store each of the nodes in this array. For example, we will initialize it to 4n, and so the question is in which index we will store which node. So for that we have a quite efficient formula which is also used in heaps, so everybody knows about it. So the root will be numbered as 0, and its children will be numbered as 2 into 0 plus 1 and 2 into 0 plus 2. So basically I generally implement segment trees in zero based indexing format. You can do it in one based indexing as well. In one based indexing you just don't add one here, you just add one here, because it will be, if with the value, if the index of this node is 1, then it will be 2 and 3 like this, so it doesn't matter. So like this we will number the indexes. Okay, so we also understood that where we will store all the values of the nodes. So the root node basically will be stored in a segment tree of 0. This is the root node will be stored. The child means root of left would be stored in segment of 1, like this. Okay, so we will store the entire tree in this vector. So like this we will do. And yeah, so I'm not explaining it here in detail, so I'm explaining you the operations. Like when we are asked summation between L and R, we just do a search on this tree, and it basically takes logarithmic of n times to actually get the summation. And whenever we are updating index and value, it is also logarithm of n, because you can see that it is almost it is actually a balanced tree, you can say. Not exactly balanced, but yeah, we can approximately say it is a balanced tree. So both the operation can be done in logarithm of n time. So the total time complexity would be first the order of n for building the tree, then for q queries it will be logarithmic of n plus logarithmic of n, like. So this is the overall time complexity, which is a lot better than our older method, because in our older method, if we first compute the prefix, this is with segment tree, this one is with segment tree, and this one is with the prefix method. It was good when we were not updating, but when we are updating, it becomes q for order of n, and it will be order of n. So you can see that it will be q into n. So this is not an efficient method. So this is a more efficient method, but the one problem is that it will take order of n extra space. It will take 4n extra space, but still it is worth it. Okay, so now we are returning to our problem. So let me recall that what was our problem. So for a particular node, we need to tell how many nodes are actually greater than this node. So we can implement a segment tree to solve this problem, but whenever we are implementing a segment tree on while we are doing a DFS, it becomes a little bit complicated. So I will try to explain it in the most simple way possible. 1 second. So what we will do, so I guess you have understood the brute force, and I know I don't need to explain it again. So let me start with the segmentary one. And oh sorry, I forgot to show the operations. So let's say we want to update a given value. Let's say this is 6. Again it is this is 6, and we are making it 10. Now how many nodes will get updated? So this node will get updated, this node will get updated, this node will get updated, and this node will get updated. As you can see, it will be always logarithmic of n times, because we are just starting from the root, and we are just starting from the leaf and going towards the root. Okay, so for update operation, the time complexity is approximately logarithm of n, and whenever we are doing a query, let's say we are querying from 0 to 3, so we first go towards the node and we see that what is the range. So we can see the range. So what is, yeah, it says 0 to, so this is representing summation from 0 to 6. If our query was it means if our L and R, so what I mean by, yeah, this one, if our L and R were 0 and 6, then we probably would have returned from this node just directly, we would have returned. So it would have been order of one time, but it always will not happen, and we have to traverse a little bit, we have to traverse the segment tree, and the average and the worst case time complexity would come as log n. So yeah, so what I was, yeah, so we need to find the summation between 1 and 4. Now we see that we are at 0 and 6 index, means we are at a node which represents 0 to 6 index. Okay, so what we will do, we will go in both the directions. We will go here and we will go here. Now we can see that this is 0 and 1. So this is not a proper, like, this is not a proper segmentary. I am just explaining in such a way. Means just I want to give you the intuition. If you don't know that what a segmentary is, then you can just skip the you can just skip this video. Maybe you can search a Geeks for Geeks article, or I will upload another video which will be dedicated to segmentaries only. So yeah, what I was saying, we will go here and we will go here, and we will see that 0 to 6 is being completely overlapped by this interval. So we will just directly return. So this is how the query operation will be, and so we have like this we will call our query. For we will just, so let me write the query. L, sorry 0 to n minus 1. Wait, let me write and then I'm telling you. Yeah, so this is how we will call the query, and this 2 represents the what can I say, the actually the lower bounds and the upper bound of our array, and this is the this is the lower bound and upper bound of our query. So we will just provide this information to the query function, and summation of this one will be provided to us maybe in x. And for update we will just, so I forgot to explain you what the 0 is. So this 0 is actually the index of the segmentary. These indexes are the indexes of our array, and this index is the index of our segmentary. So what yeah, 0, like I have already told you, this is 0, 1, 2, so like this. So this is the index of our segmentary, and for a node we have two types of information. One is the index of that node, the index of that node by which we can search the node inside the segmentary. So index of this node, and another information is the range that it is representing. Let's say it stores the value of the segment 2 to 4. It is 10. So and the index is 0. So basically, which means it is the root only. So mostly we name root as 0th index. So like this it will be done. So for update we will so for update what we will do, this is the our segment tree index. So why we are putting 0 here, not any other number, because this means we want to start searching the segment tree from its root, because we want to explore all the possibilities and all. Okay, so and here we will give the entire bound of our array, and we will be provided with an index and a value. So this is how we can update. And after this operation, the means at index, the value will get successfully updated, and all the necessary changes in our segment tree would be made. So yeah, so I overall explained what is the segment tree and all. So now let's come to this problem. So maybe most of you are thinking that how we will implement segment tree to solve this problem, because it is a completely different problem. So before explaining this problem, I want to tell you about a problem which can be solved by merge sort as well as segment tree. So the problem is count inversion pairs. After I explain you this problem, you will just take a second to understand our original problem. So in this problem we have an array. Now this is a quite standard problem. So AI represents element of an ith element of our array. This is our array, and so we need to tell that how many of such pairs exist. So this is quite a trivial problem. If we traverse loop wise, then it will be order of n square and all. Like most of you have been taught in college that it can be solved by merge sort, but we can also solve it using segment tree. So in segment tree, in segment tree we can solve this problem, but the time complexity will not be as good as merge sort. Because why I'm telling you this? So the main technique of solving this problem using segment tree is that we will first take an empty segment tree. We will take an empty segment tree, and we will not perform any kind of build operation on that segment tree. Let's see if it is 1 second. Okay, so we will just initialize the segment tree. So this is a modified version of our standard segment tree, 4n plus 1 0. Plus 1 is basically done to avoid any kind of overflow, but 4n is pretty much safe. Okay, so this is our segment tree, and now we will keep inserting all the elements till here. Means we will insert all the elements in our segment tree, but this insertion will be little bit different. So this n is not the size of this array, but this n is maximum element of this array plus 1. Yeah, so why I am doing this? So you might be familiar with this technique, that whenever we compute a frequency of elements, we just take an array. I'm saying that if maybe mx is a small value, mx is greater than 100 is greater than equal to mx, and we are given certain values, and we need to find the frequencies. So when we are trying to find the frequency of 10, we are going to the 10th index and just doing a plus 1, means a10 plus equals to 1. Like this, we will extend this concept to our segment tree. So how we will do it? So we know that this segment tree is completely empty. This is the maximum. So I want to tell you that this array actually does not exist, but we are just building a segment tree. See, these nodes actually exists, but this array does not exist. This exists. I'm just taking you I'm just drawing the array to explain you, nothing else. So see, why this? No. So initially it will be 0. Now whenever we are let's say, okay, so let us solve it in a different way. 1 second. 0. Oh, whatever we can take whatever values we want. Okay. So yeah is greater than is I greater. Let's say we can if we are if we were solving this problem, then probably we need to start from here and go on, okay, but yeah. So here our array is completely empty. So 1 second, let me write the equation. ai greater, ai greater than aj for where I is greater than j. Okay, so this is our equation, and yeah, so we are at this index, and at this index we are it is trivial that the answer is 0. So we do nothing, we just move to the next index. At this index we will update our 0 to our segment tree. This is interesting actually. So let's us mark all the indices. Okay, so 6, yeah. So we just go to the segment tree. So this is the second index, and we update this node, not this node, because this array does not exist. Okay, so we just eliminate. So we just replace 0 with 2. Means this second index with +1. So the value of this index becomes 0. This is all 0 0 0 0. Now after updating this, we check that from so now we check what are the elements that are less than 1, which is already present in our segment tree. So which is we will query. So this is very interesting. So we query 0 to mx, obviously, because mx is the upper bound of the data on which we are building the segment tree. Mx from this value, means the lowest value, to this value. And when we are doing this query, we will get our answer as 1. So we will do an answer plus equals to 1. Now let us go to the next index, and whenever we are moving from an index to another index, before updating that index, we will just before updating this particular index, we will perform our query operation, and then we will update, because if we are updating, then some inconsistencies, and we may get wrong answer. Okay. But it will not result in wrong answer, because even if we are querying first, then even if we are updating first, then 3 is equal to 3 and it will not be computed, because for example we are at this position and we are doing a query from 11 to 0, and so 12 will not come. So yeah, we can do it in any way. This is our wish. So whenever we are coming to 3, after querying, we will update it, and we will move to the next. Whenever we are at 10, we will do a query from 0 to 9. Now we have already incremented our 0th index, see, 0th index, our second index, and our third index, right, +1. So whenever we are performing the query operation in this range, we are getting 3. So we are answer plus equals to 3. So like this, for each index we are doing one query operation and one update operation. So our total time complexity will be order of n into log n plus log n. I don't know why it is lagging. Okay, so we will do it like this, one for the query and one for the update. So if you did not get it, I can totally understand. If you are here for the first time, you will not understand. So 1 second, 2 3 4. So I am taking another example to explain you. 1 3. See, what is the maximum value? 7 is the maximum value, right? So we will update it. This is our segment tree. So I have told you these are all 0 0 0 like this. So whenever we are at this index, we will update it in our segment tree +1, and we will move to the next index. And now at this index, we will see that how many elements are present in this segment tree which are lesser than this value. So you understand that the range would be 0 to 2 means 3 minus 1, which is 2, obviously. So now I think you understand. Like, we are going to this index and we are storing this entire thing. We are going to this index and storing the entire thing. And from 6 maybe we are querying. Querying 5 to our from 5. The range is 5 to 0, and we are getting the answer as 4. So now you understand that why it is so why it is order of n log n. Okay, so now it will be very trivial to solve the original problem. Now we have our tree where we will need to find the total for each node. We will calculate total number of ancestors which have greater value than our current node. So 10, let's say 2, let's say 3, 1. Now what we will do, whenever we are entering, we will store this node, means the value of this node, to our sum segment tree, where the segment tree's value will be the maximum, maybe the maximum, as I have told you. Similarly, we will store all this, and whenever we are at this index, we will see now the type of query will be little bit different. So we will query from 2 to max, because we want to know about the greater elements. See, in this example, we were looking at the lesser elements. The lesser elements means AI is the index, and how many elements are lesser than this we were querying. That's why we were doing it from 0 to value -1. Where value is the value of this index. Okay, so let's see. Yeah, so whenever we are at this index, we will see, we will just add 1 to our value mx, and we will perform a query on our segment tree. And whenever we are going out, we will just perform an update operation where we will decrement the value. Whenever we are coming in, we will increment the value, and whenever we are going out, we will decrement the value. So I am taking an example to explain you this. So I guess most of you have already understood by now, but let me take an example. Let us take a small tree. Let us not complicate things to 1 5. This is 5 8 9 2. Okay, so the max element is 10. So initially we will just initialize this segment, nothing else. Yeah, 0 1 2 3 like this. We will initialize this segment all with zeros. 0 0 0 0 0 0 0. Okay, so why I am explaining you this problem, this has come in our midterm exams, and I found it pretty interesting. Okay, so yeah, so now we are starting our depth first search. We are at 10. We search, see, whenever we are at a current node, we search for we search how many of its ancestors are greater than this. So since this has no ancestors, our segment tree is initialized with 0, so our answer will be 0 for this. So we will create a answer vector where for all the indexes we will store the answer probably. So let us consider it as 0, 1, 2, whatever, like let's say see, the actual problem was what we were given in the exam. It's like this. See, the range was given as 1 to n, and the range was given as 1 to n, and we were okay. So one second. Okay, no. Okay, so yeah, so I forgot to tell you what the time complexity is. The time complexity is actually order of n into log of mx, not n, because we are building our segment tree on this entire array which is of length mx. So I forgot to tell you this. So similarly, if the range is from 1 to n, then what we will do, 1, 2, 3, 5, 7, and one second, how many okay, so 7, 6 maybe. I'm just explaining in a rough manner. So yeah, mx will be, our mx will be 8. Okay, so this one we will see, this is our answer array. We will see that how many we will store answer of each node inside our answer array. So this is our answer array. Okay, so we will first query from 0 to mx, we will query, and obviously since the summation it will be 0, so we will store 0 here. Now we are going here. Okay, so now second index will be incremented by 1. Second, I'm not drawing the entire tree as I've already drawn the entire tree, and I will make a separate video for segment tree. Okay, so we will increment 2. Sorry, not 2, sorry. We will increment 1 and we will go to 2. Now we will search how many elements are actually greater. We will find that no elements are actually greater. From 3 to mx we will query. So again we will store a 0. Now we are at 3 and we are updating 2. Now we are updating 3. So at 3 again we will search, and 1 or 2 are present. For 3 we will query from 4 to mx, and again it will be 0. And 7 we also, for when we are going inside 7 we will update 3, and again it will be 0. For now what will happen, say this is now we have no further nodes to go in this way, and we will backtrack. Whenever we are backtracking, we will subtract it from our array. So we already have updated, right? 7 we have updated when we went inside this node. We updated it to 1. Now when we are moving out of this node, we will just do a 0. We will just decrement the value. When we are going out, again we will decrement 0. Again, now we are going here. Now you can see that this path's information is stored in our segment tree. So like this we will keep doing, and whenever we are at 4, 6 is greater than 4 obviously, so we will search from 5 to mx. Okay, 5 to mx, and it will be 1, the value will be 1. So like this we can find out for each of the nodes, and the time complexity will be similar to the, sorry, maybe there is some lag. 1 second, why is it lagging? 1 second. Yeah, so the time complexity will be similar to our inversion count problem. It will be order of n into log of mx, where n is the total number of nodes, and mx is the maximum element of our array. I hope you understand this problem. So this algorithm is efficient when mx is comparable to n. When mx is comparable to n, it is a pretty efficient algorithm, because when mx is equal to n, then we would be able to solve this problem in order of n log n time. Okay, so I will make a separate video for coding this up. I will code the entire segment tree and I will solve this problem. I will take the input. I will show you how to take the input for a tree. Okay, so I think you understood it. So it was a little bit complicated when we are combining segment tree problem with a normal tree. It becomes a little bit complicated. In interviews you might be asked about the time complexities and all. Okay, thank you.